Right, good morning. It's my great pleasure to introduce Fawzi Mohamed. So like myself, Fawzi started his studies in physics at ETH, but then he switched to a new degree, which is called Rechnungsgestützte Wissenschaften, which translates to computational science.
And engineering. The official translation is.
And he then went on to do a PhD in the group of Metainfo. Amongst other positions, he has worked as a software engineer at Nokia in DTF Germany. And in 2015, he joined the group of Matthias Scheffler at the Zauber Institute in Berlin, my hometown. And I think it's fair to say that Fawzi is one of the key architects of the NOMAD infrastructure. I got to know him via the Optimate consortium. Optimate is a group of developers of basically all the big materials databases worldwide. Materials project is there, NOMAD is there, materials cloud is there. And yeah, from talking to him and also from his inputs to the workshop, it was always apparent that Fawzi has thought a lot about many design aspects of NOMAD, and so we are very happy that he could make the time to come here today and to prepare a talk about a slightly unusual topic maybe for him, which is workflows in NOMAD. So let's welcome Fawzi here, and I'm very much looking forward to this presentation.
Thank you very much for the kind introduction. I'm very pleased to be here. So yes, workflow in NOMAD. NOMAD is not so much about workflow, but we will see what we have. So in the NOMAD, probably a lot of you know it is a center of excellence, and it's a new project with 8 research center. And for supercomputing center, you see a bit what is there. Officially, the project NOMAD, the COE is finished. Now there is something called FAIRD, and there is still some work going on, but the COE itself is finished. So what are the goals of the NOMAD COE? Some align a bit with what is done here. So we know that we have more than 200,000 material that are considered known, but the basic properties are known for a few of them. And it's highly likely that there are materials with superior properties. And NOMAD was Novel Material Discovery, that was the acronym back then. So the idea was to use, or is to use, big data analytics to identify trends and anomalies in material data. And obviously here the first step is to make the data available, addressable, and organizable. And in NOMAD itself, there is a thing called the NOMAD archive, and the NOMAD archive goal is exactly to make the data available. The data of simulation code used in the community and available to what? To the encyclopedia, to visualization, big data analysis, and also to any external users. And the data comes from the NOMAD repository. So the question is then, what is this NOMAD repository? And the NOMAD repository, you have there the link, you can go to look at it. There is also a funny movie that I won't show, but shows a bit the idea. But it's a repository for computational data, material science data, especially ab initio and atomistic simulations, that guarantees storage for at least 10 years and supports 40 computational code, and was started by FHI, Humboldt University, and the Max Planck Computation and Data Facility. So the repository collects data from all over the world, and this is already a very large difference from AIDA. So we start with data that we haven't produced ourselves in big part. So it's very different from starting and producing the data for your purpose and then working with the data that you have produced, whereas you get data from somewhere. Some part is also produced by you, maybe, and you will also produce data, but there is also...
There must be a microphone on somewhere, but this one, it isn't. Maybe just stay a bit away from it.
But I have to turn.
Sorry. Okay. Do we have a... Can
Okay.
you point
Okay.
over it? No.
Okay, now it seems to work now, so let's hope it works out. But so the thing is, we don't start with producing data. So workflow in that sense are not really the topic or a big topic in NOMAD, but big data is not only large amount of data, but also robust tools and workflow. Because if you don't want just to produce big data, big amounts of data, but also produce it in a reliable way, and so that problems can be found and fixed, and probably also hopefully get then the fixed data integrated again with so that you have the clean data to work with. And if that's the case, then obviously naming and provenance, something that is big also here, has a big importance. It's very important. And we require the naming and provenance about the source of the data, and also to describe the data itself that is produced. So what are more or less the philosophy of NOMAD? Some things align very well with here: scientific openness, open access to everything, allow others to develop alternatives. It shouldn't be a closed thing that then, if you don't like what is there, you cannot do something else. Track origin and cite original contribution, and trying to develop APIs that should be used because they are convenient, not because it's the only option. And for example, all the low-level bulk data is also shared in a as file in just that you can download and get everything. So you can get all the data that we start with, which is the open access data of the NOMAD repository. And this data, I have an old slide, but it's just to say that we have some data there, mainly from Flow, QMD, CCBDB, and Materials project. This consists of zip archived, compressed data. And yes, we have 4 million energy calculation and so on. It's just to say we do have quite some data in the repository. The funny thing is it's quite some data, but typically it's never enough when you look at something specific, because the problem space is so large that probably if you are looking to to something specific, it's not there. So obviously, big data is also about having really something that can scale and handle a lot of data, and this means that we have that we need an infrastructure to do our conversion and preparation of the data that scales, and for that we use a RabbitMQ to queue system, Docker container, and Kubernetes. And yes, we can then look a bit later. I will go a bit more in details about that. But the source data first is the public data from the NOMAD repository, as I said. And these are archived using the Begit format. Begit is basically a zip file. And it's a format that was developed initially by the Library of Congress to share data. And it consists of a zip file plus description of what inside and a directory that contains all the data. And we prepare all the data in this format. And by the way, the use of zip is not an error. The beginning I was thinking tar.gz or something like that, but zip has an index that lies at the end of the file, so you can extract quickly any piece of the zip file. In tar, you have to scan through the thing to extract data. And that's also the reason Library of Congress that cares a lot about long-term storage. It has checksum for every file, and everything is checksum so that you can verify if data got corrupted and so on. So the start data is immutable data that is put in this Begit format, and it's never touched again. That's the idea. We start with something that is preserved long term, and the name of that depends only on the content of the archive. So we call it archive GID, some R plus 28 character, a checksum. And this gives us host-independent URI to refer to any piece of data. So inside the source data, you can define any file through archive GID and the path inside the archive. And this means that no matter where this was generated, you get exactly the same. So this is an important thing if you think a distributed environment. At the moment, mainly it's the NOMAD. There is one website for NOMAD and so on. There are some things around, but not so much. But if you do the same thing somewhere else, you should get exactly the same thing. And this makes it that the data can be distributed and the work distributed, and it works well. So it's host independent. You don't have something that it depends on the NOMAD at MPCDF, but it can be anywhere. And it's a clear naming. We have a clear naming of the program that transformed the data. So if you have the initial data, the input data has a clear name now. And then we transform it and we extract the data. And the program that does it, we also have a clear name of the exact version. And to have that, we use git describe. Git describe gives you the exact, starts with tags, and then for every check-in in the Git, it has a unique identifier. But still is nice for human, because what you really want is the so-called semantic versioning, where you have major version, minor version, and so on. If something changes, you have a new version, you have an idea, does it break everything or not? Maybe it still breaks, but you have some guideline of what to expect. And this gives you the best of both things. And if you have these things, you can do things. I want the parse data that comes from archive X and was produced by Parser X at that version. And you can also say replace or compare the data with one that was produced with another version. So you can begin to talk about the data. now this is just the source and the transformation, which is an important part, and is also important for AIDA to have these two pieces. But that's not really enough. We want to provide then the data that we generate to make it usable. So we have definitely to describe also the data that is produced. And that's the Metainfo. Metainfo is the conceptual model of the data that we produce. And it's language and format independent and defines how the data that we extract is organized. And this is important both for human and for machines to know the data is organized, is structured in this way. When you talk about this, often the concept of metadata comes in, and we call it Metainfo, not metadata. And the reason is metadata is data about the data. And data about the data depends on what you consider data. And it's not clear exactly what one wants to consider data and what data about the data, because it's data, also the data about the data is data. And there is the RFC, there is a standard, the Dublin Core metadata element set. And there, for example, that's what librarians use. The author, the title, and so on. This is considered metadata. But for us, the author, the name is data. And the fact that it's an author is the metadata, is how we structure. And so to avoid misconception, we called it Metainfo. And the Metainfo, in the Metainfo, the data are values of physical quantity or setting of a computational method. And these are numbers, strings, Boolean, reference to other group of data. So we have a relational model, or multidimensional arrays of these. These are just the data type that we accept, which are very simple. And then the metadata describes and organizes the data. It has a unique name for all concrete quantity and the groups to use them. And it uses just alphanumerical character and underscore. It's organized in a hierarchy, in a tree. And it has a single public namespace and semantic versioning, so that you know this is the same version, this changed a lot, and so on. Here is an example. As you can see, these are some data. For example, program name, it's FHI aims. And in red, the part in red, FHI aims, are the values. Is the data. Program name is the metadata. So that describes what FHI aims is. And so it's not just the name, program name, but it's also the structure. It's inside section run, for example. The fact that it's inside section run is describes also in the Metainfo. And then we have something that we call section system. The section are to group set of data values together, so like a dictionary. And for example, section system describes the geometry. And this has together the simulation cell, the atom position, the labels. And the method describes the method used. And in the Metainfo, you also have the default units that are used. Because if you have just a number, you should know what it means. And a very important section is the section single configuration calculation. This represents a single calculation. In it, you see energy total, which is this number. what this number exactly means depends on the method. So we try to reuse the name. One option would have been we use the MP2 energy, we use couple cluster energy, we use DFT energy as separate entries. It's not what we do. We have energy total in a single configuration calculation, and the method says this is a couple cluster calculation. So we try to avoid having too many entries in the Metainfo. So it groups together values with section. It allows one-to-many relationship, and it groups together similar types also, making them come from the same abstract type. Here is what then we gain. The Metainfo structure the data, so we start with the calculation from the repository, which are just files and are in many different formats. And then we try to bring it in the structure given by Metainfo. And this we call parsing, this step. And then this can be mapped to several file formats, because the Metainfo tries to be an abstraction, not tied to a specific way to store the data, but to give enough structure so that you can sort of work with, but still you can then store in different file formats, because every file format has different trade-offs, and one uses very little space, another one can be read by human, one can be transmitted on the web easily, and so on. And by using the Metainfo, we don't have to choose immediately which trade-offs we are doing. We try to represent the data, and then we go with what exactly, which format to use. And in that part, we have this parsing. It's a crucial step. It's mapped the raw data to the model defined by the Metainfo. So it requires knowledge of the simulation method, and we wanted to support many codes. It means many parsers. And here I should really thank all the people that worked on that, because that was a lot of work, and you see a lot of people that really contributed to developing the parsers to enable this thing. And this is more or less the workflow. We start with zip archive that contains directory and files. We do the parsing, and through the Metainfo, we can map it to files that we call the parse data. We normalize it. Again, through the Metainfo, we mapped to HDF5 and Parquet. And in the end, you have an API that lets you access the raw data, the parse data, and the normalized data. For example, get the result in JSON. And the user, if he has the model of how the data is structured, he knows which queries, which kind of queries, or which data he can extract. He can ask for it and then get it. The Metainfo was produced in a so-called a posteriori way, because it's difficult to define things without being grounded on something concrete. Many of the previous efforts were starting thinking about what is a calculation, which properties they have, so in abstract. And very often you can then build something that doesn't match well what is used in practice. But here we started from the data that we had there in the raw data, and we tried to find a way to classify it and build it. And so the Metainfo stems from the data in the calculation codes. And the Metainfo is in a Git repository. In practice, the Metainfo is also described using a kind of JSON dictionaries and so on. In fact, the Metainfo itself can be described using the Metainfo. And we also have a Metainfo description of the Metainfo itself, so it's recursive in a way. But here is an example of the program name. You see it has meta name, its program name, meta description, specify the name of blah, blah. The type, it's a value type. And we have 4 types, the concrete values, the section that group the values together, dimension for multidimensional arrays, and abstract types. Abstract type, I will go on in a bit, but here you see we have a Git repository where these definitions are there, and one can look at them, can modify them, and they are interpretable by a machine. And a very important aspect of this is that the Metainfo uses a so-called open world access, approach. It can be extended by outsiders. It's easy to add data. So basically, you define a data, and then you say its context is there. So if you look in the previous here, you see you have a super section run. Here it's where this data type, which is a string, lives. So you don't first describe the outside, the context, and this section can contain these things, but you go the other way. You say these things is in that section. That seems a small change, but it means that you can have extra definition, new pieces of data that are defined in a separate file, and they are just added to an existing section. So this makes it more flexible, more extensible. And this comes from the idea that we started on data description, not on validation. Many of the other things that you look are validation tools, are trying to define how the data should look like, so schemas and so on, and they go the other way. And here we start from the data, and that's something that I feel it's an important aspect of what we have. And obviously, if you have something that can be interpreted by a machine, you can also have a browser that is a bit nicer for human to use. You can go there and search for one of the Metainfo. You can find the definition. You can find how it relates to others, and so on, in a nicer way. The last thing that we have are abstract type. Abstract type are things that are used to classify the Metainfo itself. So this, for example, is a settings that relates to key points, for example. You can have values in the settings that have this meta abstract type, and knowing it can be useful to find settings that are code specific, because sometimes you have different code have strange settings that does something. It's important to know if it's the same or if it's different, or that it changes that thing, but it's code specific. And by using the abstract type, you can sort of classify also these things. And here is in practice. So we use the Metainfo to describe calculations. And this is what we came up with. Let's start with the center. Section single configuration calculation is basically a single point calculation. We saw it before. And it has a section system, that's the geometry, and the method, which is the description of the potential surface. It can have constraint and topology, but these are more for the force field methods, typically. And then the single point calculation are structured in a frame sequence and that says, for example, this is a Monte Carlo simulation or NV calculation, NVT calculation. And if the section sampling describe this is an NVT, for example, MD calculation. And the frame sequence contains the frames itself of the calculations. So this is the high-level view. And just so to remember, this is just a small part of it. And you see this single point calculation, method, system, and we have a reference between them. So we have seen workflows, but the workflow was more or less our workflow, the parsing itself. This is not really what AIDA workflows are. The workflow that you are more interested in are things where you do first minimization and then, for example, phonon calculation, for example. These, the way they are solved, are as a reference between calculation and run. We have this object, the calculation and the run, and this calculation can say, I'm derived from that other calculation, or I come from that other, for example, using section calculation to calculation reference, and it also, you specify the kind of relationship that you have between the two, and that's basically how workflow can be represented. And workflow inside a calculation are pretty well detected, but we have problems detecting workflow. In some cases, it will be nice, and we do use, when we can, checksum to see if it's the same configuration or same method, or maybe if it's close by. And I think that it's very useful is if the program that does the simulation actually puts a unique checksum in all the files, so that you are sure that the file lying there belong really to that run, because sometimes you have someone that restarts, files gets overwritten, and then it's difficult to figure out what happened. And then that's what you get if you get data that you haven't produced yourself. So what we can only say is try to convince the developer to put more of this checksum in the file, so that it's easy to connect them and find for sure the connection between the files. So I hope if there are developers here that they think about developer of codes about keeping this kind of information in the files somewhere. And another thing that could be done is extract the workflow info when available. Currently, we are not doing it, but that's obviously an obvious step, like if it was done with AIDA, to try to extract the workflow directly from there. when you have the data, a description of the data itself, we also have what we call the NOMAD URIs. We have data identifier. I said we have a unique identifier that define the start data, the archive, but also all the pieces of data in the NOMAD metadata have a path because we have a tree structure inside. So if you say from this calculation, and it has a unique ID, that calculation, I want this, and you give a path in the Metainfo, for example, section run, section single configuration calculation, and you can uniquely identify any piece of data. And using that, you then can build software that modifies the data, extracts this data, queries this data. And we have a REST API to access that, and you can go there. I think we have enough time, so I can quickly. So the NOMAD COE, there is big data analytics, and then the query. Oh, not now. No, I don't try. I will try later to reload. Just now, I did it before. So you see, I did just a stupid query, and the query itself, I will try again in a moment, but just to be sure that I have connection, I first show the things and then I try. So you have result, and you see this NMD something which looks pretty ugly. These are the IDs, the unique IDs, and using that, it's possible to go and get to any level of any eigenvalues occupation, for example. You can go through it, and it has here this URI. It's a unique identifier that lets you go to exactly that thing. So in the API, you can just, for example, paste that thing, and you will directly get to that single piece of data. Obviously, having having this is let's see. So you see that you get to the single piece of data using any URI. And here, just so this atom species is obviously a meta described in the Metainfo. You can look up what exactly it means, and here you can put. I should reload and see if things work, and they do. So they don't work. Why? I'll try later. But the low-level access to all the data, as you see, works. And let's go here. The metadata is like a language. If you have more data, more tools, it's more useful. If it's simple, it's more useful. But having more constraint can make it more usable in other contexts. And the NOMAD COE didn't just contribute for. I'm just wanted to show another thing that might be useful for AIDA is the container manager, which makes arbitrary web application running in a separate Docker file for every user transparently available. So that, for example, you can have Jupyter things. And the way it works, it's you authenticate a user, start the user specific Docker if required, forward all user requests to his container, and then here you have a description of how exactly it works. And with that, the infrastructure, low-level infrastructure was developed by several people, and also the repository itself, and Parser Development. I already thanked all the Parser developers. I want still to acknowledge Matthias Scheffler, Luca Giringelli, the whole NOMAD team, you for your attention, and then say that we received funding also from you. Yeah, that's it.
Thank you very much, Fawzi, for this very insightful presentation. I'm sure there will be lots of questions, and thank you also for staying perfectly in time. I come to you in a minute.
Hi, thank you very much for a very interesting talk. I have a bunch of questions. I'll try to keep it to one for now, so I don't get a chance. I was wondering about the parsing.
Yes.
As you said that you implemented the parsers, so there's now a subset of codes available. I take it though that even within a single code, let's say the parser for FIHI aims, the users will often have liberty to rename certain files, for example, the input file or the output file. So how does the parser even detect that they just dump their calculations there, which files actually?
That's actually the hard part, and that's where I was saying detection and having, for example, a new version of FHI aims generates a unique checksum for run and puts it in all the files at the beginning. So that helps a lot. Otherwise, we have some kind of heuristic. The thing is, if you get it wrong, sometimes we don't detect. We try to be more, if we are not sure, we look also at modification dates, which we preserve. So to be able, creation modification date, if they are very different, then you say, oh, probably this doesn't belong to it. There is no absolutely foolproof way unless the code really has unique identifiers inside the files that you can really track. This is run X, and then at the beginning of every file you have.
So if I understand correctly, this is what you were referencing to in trying to detect the workflow. So connecting multiple independent.
Also, yes.
I was actually talking even within a single
yes.
aims calculation. How would you know which file is actually?
As said, the current version of FHI aims generates at startup a unique identifier, and then all the files have this unique identifier somewhere. All the dependent files.
You know which files belong to that calculation, but I'm more, for example, the input file can be anything, the name of the input file. And presumably the part or the output file and the parser should be looking,
yes.
okay, I want to parse the output.
So FHI aims and CP2K and so on, by default, they write again the input file in the output file. In that case, that's the one we take. If it's not there, because it can be switched off, then we try to guess.
And for the output file, do you start parsing?
For example, one of the worst is Quantum Espresso, where you typically go from standard in even, or you don't know exactly, and then
okay, so
it's a challenge. There are, yeah?
I think we should give
So my question is, what is the meaning of data analytics?
I think you have to speak up a bit back.
So that's difficult to think. Basically, what we do is we try to provide several tools like subgroup discovery, like the thing for neural networks, several libraries and so on, give you a notebook where you can do whatever. That's the container manager can start up just for you a thing that has these things available, has a data part of the data that is just for you where you can write, plus all the other data as read-only, and then you can do.
You mean you can do numerical processes on those?
Yes. So you can do mainly what we think is after extracting the data that you have in calculation and then doing some analysis on the top of it. And typically you want to give as much freedom as you want because you don't know exactly which kind of analysis. There are some examples. If you go to analytics toolkit, NOMAD COE, there you see some notebooks that do kernel ridge regression. I don't know, or do some neural network fitting and then using for prediction. These kind of things.
So you say that everything is from the data and not from a schema. That when you have the API and have everything, right? You start from the data, and then the data determines the schema or the output.
Well, we built our Metainfo having the data there that we wanted to fit to it. So we didn't try to first think how can calculation look like and so in abstract, but we had already data. Obviously, you go a bit both way, but in the end, what you create is the Metainfo, which is basically a schema, but an extensible one, yeah, and a bit different how you.
Which looks like an ontology kind of thing going
yes.
on, and then
yes.
a lot of stuff. So in the end, then you try to afterwards. So you have the data where you then get your new schema Metainfo from, and then if you get new data in, you try to match this onto what you have, or you
yeah. So the schema that we produce is we try to abstract as much as possible and have a general thing that works for all the data that we have. And a new parser typically tries to map to what we already have. If he cannot, he has extra things. Typically, he had code-specific things. He can just add those things. And if several Parser Developer add the same thing, then we say, maybe we should move this part in the common definitions and standardize it so that it's used by everybody. That's basically the way we went, how it grew. And yeah, basically the extensibility is a very important part of this process, because the Parser developer can immediately add new entries, even adding to the same section new values, and then that are code specific. And then when he's done, he says, oh, I think these are actually more general. And then we say, oh, okay, yes. Or maybe two did in a slightly different way. Then we try to get it to the same way in the standard. And so that's the process. And then the common part grows and covers more things.
Okay. Thank you very much. Thank you for the talk.
Before I get back to Sebastian, I also have a question. So you introduced this Kitabi container manager,
yeah.
right? So can you spend a few words on how it compares to Jupyter Hub? Does it
Yes.
use Jupyter Hub?
No, it was done before Jupyter Hub. So actually Jupyter Hub is kind of similar. In the end, they use a very similar approach. We used Node.js to do the forwarding with HTTP proxy library, and they use the same thing. If you use just Jupyter, maybe Jupyter Hub is better, I have to say. No, not. I haven't looked a lot to Jupyter Hub, but if I would have to choose, maybe if it's just Jupyter, now I wouldn't choose my thing because it has a larger community, there are more things. But the advantage of the container manager is that it's not tied to Jupyter in any way. We have Credo, for example, that is the thing that is used for subgroup discovery, where you search for in the data. Instead of having a global model, you try to look at some subset of the data that is well fitted by a simpler model, and find outliers or find things in subgroups. And this was developed completely independent, doesn't use Jupyter, and we can use it just the same, because the idea is we have a template, and that generates the YAML file that Kubernetes needs to start the pod, looking at the user plus the things. It fills out this template and then creates that pod if it's not there, and then forwards all communication apart from few URL that are used for management of the container manager itself. Everything goes to it, so it's transparent. It doesn't really expect any kind of special thing in the URL. It forwards basically everything to your container. And this means that you can have any kind of web service running there, and so it's more flexible. It's less tight with Jupyter, so if you have already Jupyter Hub and all the structure there, maybe that will be a better choice. But maybe not, so look into it, because it's nice what we did there.
Thank you very much for a nice talk. I just wondering about the data part. Maybe I missed this point, but what I understood, you use kind of predefined schema on how data should look like. For example, CPTK has a specific output, and you know how they look like in the part. But either consider the use of a kind of machine learning to learn how the data should look like, and then extract the data from that?
That cannot really work, I think. because there are machine learning can work for languages where you have a lot of redundancy, or when you have a given structure and you can find out things. But for data that are just number, you don't know the units, you don't know exactly what it is. If the people put some labels, maybe you can sort of figure out. Because the label is there, then you have to try to find out the units and how it's outputted. But I wouldn't trust at all what comes out of machine learning there, because there is, in most code, some code are very nicely done, and then you could use machine learning from it to it. But in most code, it's too messy. And you have also extra files, and they are written if that thing is there or not. And you really need an expert that knows a bit the code to say, oh, this thing is that. And here you have the SCF cycle starts here, ends here, and so on. So you could mix and use machine learning to help you then help an expert doing it faster. That I could see, but doing it unsupervised, I don't think it's really doable.
Last question.
So my question relates to data migration. You were discussing, so we have these, the schema, the Metainfo that allows users to target and query for specific data.
Mm-hmm.
But to do so, they will have to have that exact name, because otherwise they won't be able to find it. But at the same time, you also said that this can evolve while data is being parsed. So now imagine the situation where you already have a lot of data with a specific key name. The parsers see some common ground and they decide to come to a new name.
No. While the data, a given parser version has a fixed Metainfo. New parser version might have a new things. We don't evolve while parsing, and no, it's already an issue like that. And we try to be as much as possible backward compatible. So meaning a key, once it's there, will not change its meaning. And we can add new keys, but we try not to remove. We use semantic versioning for that. So it means we hope we never ever will upgrade the major version. We don't know, because we had to change the major version while developing and so on, especially when the force field code came in. We had to look again at some assumptions we had done that were not so good, and then we decided to do breaking changes.
So you reparse all the existing data with the new parser version?
Yes.
The old version becomes essentially obsolete, or is it still searchable?
No. The current thing is the old version is kind of discarded. You can still get it if you want, but it takes quite some place. We might keep one version back or so, or two, but then we don't, we really go forward. So, and if one really wants, then he has the exact parser version and so on. He can reparse with that parser and get exactly the same, or kind of exactly the same, because at least it should be deterministic. In some cases, if you have calculation, I've seen in my PhD, for example, that that's not the case. If you use, for example, the Intel libraries, they use also the coprocessor with 80-bit precision, and they lose the precision when there is a context switch, which depends on the kernel. So basically, you have in the last digits something that is really random and it's not reproducible. But as much as can be reproduced, it's for scientific reasons. So we try to be reproducible. We have the immutable start. We have the version that we know of the transformer, and then you can reproduce the same thing. We don't keep around the older data forever. We try to be as backward compatible as possible. That's what we can do. More, I think, becomes too much a burden.
No, I understand. I mean, this is a problem we have in AIDA as well. And
Yeah.
we haven't solved it as yet.
Thank you for your questions. Thank you again, Fawzi, for this great talk. Let's thank the speaker again.